Hi everyone, and welcome to the third video in the Weather Unlocked video series. This video is going to go over Skew-T soundings, and it's going to be a continuation of the previous video, which went over upper air launches. Now, in this previous video, you learned about how a weather balloon was launched, and you also learned about radiosondes and the data that they collect and calculate, and how that helps us here at the National Weather Service. So if you haven't checked those videos out, make sure to go to our YouTube channel, which is NWS Springfield, and under the playlist section, you'll see a Weather Unlocked playlist. And this is where the future videos in our Weather Unlocked series is going to be uploaded. So what is a Skew-T sounding? Well, if you remember that a weather balloon carries the radiosonde, and that radiosonde, as it is carried up into the atmosphere, is collecting data and calculating data. And once that data is then decoded, it is then plotted onto what is known as a Skew-T log P diagram. Now, if you first look at this diagram, it looks pretty intimidating because there's a bunch of lines that might not make any sense. So let's take a deeper look into what each of these lines represent so that we can understand the Skew-T log P diagram even better. So let's build a Skew-T log P diagram. The first thing we'll look at is the isotherms, which is lines of equal temperature. So each of the lines you see here represents equal temperature. For example, here is the 0 degrees Celsius line, or the freezing line. So anything that is on this line represents 0 degrees Celsius. And the temperatures are going to increase from the top left corner of the diagram to the bottom right corner. So everything to the left of the 0 degrees Celsius line is below freezing, and everything to the right is above freezing. You'll also notice that the values are skewed at a 45-degree angle, and this is where the term Skew-T comes from in the Skew-T log P diagram. Next, we'll look at the isobars, which is lines of equal pressure. So each of these lines represents equal pressure. And you'll notice that as you go up into the diagram, the distance between the lines increases from the bottom, which is 1,050 millibars, to the top, which is 100 millibars. This is because as you go up in elevation, the atmospheric density is decreasing. Now, another thing to note is that the atmospheric pressure is actually decreasing logarithmically as you go up in elevation. So therefore, the heights of the various pressure levels are now plotted as the logarithm of the pressure. And so that's where the term log P comes from. So that's how Skew-T log P got its name. Now, the next lines we'll look at are the mixing ratio lines. These are these dashed horizontal blue lines. And the mixing ratio is the mass of water vapor compared with the mass of dry air. In other words, on a plotted radiosonde sounding, it's the amount of water vapor that is in the air. Next, we have the dry adiabats. Now, these slightly curved orange lines represent the rate that unsaturated air is cooling as it rises. Now, unsaturated air is air that's not at 100% relative humidity. So what happens as unsaturated air rises? Well, as it rises, it's expanding and cooling. And it's going to cool at a rate of 9.8 degrees Celsius per kilometer. And so it's going to continue cooling at that rate until the air becomes saturated. So the rate that it's cooling is known as the dry adiabatic lapse rate. So that's what these lines represent. Now, on the opposite end, we have the moist adiabats, which is these curved green lines, and these lines increase from the left to the right. Now, the moist adiabats represent the rate that the saturated air cools as it rises. And saturated air just means air that is at 100% relative humidity. So once you have air that has reached 100% relative humidity, any further cooling is going to cause that water vapor to condense into a liquid. So what happens as saturated air rises? Well, it's going to expand and cool, and near the surface, it's going to expand and cool at a rate of 4 degrees Celsius per kilometer. However, as you go further up into the atmosphere, that cooling rate is then going to start decreasing because the amount of water vapor is going to start decreasing as it gets condensed into a liquid. So comparing the moist and dry adiabats, remember the dry adiabats are those curved orange lines and the moist adiabats are those green lines. Near the surface, the moist and dry adiabats are pretty different. However, as you go up into the diagram, they start becoming nearly parallel. And this is because once you get to very cold air, it's not going to have much water vapor because it's been condensed into a liquid or deposited into a solid. Now, the last thing we'll look at on the diagram is the wind staff. Now, the wind staff shows the plotted wind speeds and directions at the different pressure levels, and this is based on the tracked position of the radiosonde as it's carried along by the wind. Now, we can tell what the wind speed and direction is by looking at what is known as wind barbs. Now, wind barbs can show us what the wind speed is by combining various long and short barbs as well as pennants in order to show what the speed is. Now, for example, if we have very calm winds, that's typically represented by a circle. Now, a short wind barb represents 5 knots, and a long wind barb represents 10 knots. Now, an important thing to note is that these are rounded up to the nearest 5 knots. So a short wind barb can represent anywhere from 3 to 7 knots, and a long wind barb can represent anywhere from 8 to 12 knots. Now, we can also combine these long and short wind barbs to represent even higher wind speeds. So, for example, a long barb and a short barb can represent 15 knots because that's 10 knots plus 5 knots. And 3 long wind barbs can represent 30 knots. Now, once we get to 50 knots, however, that is represented by a pennant. And we can also combine pennants and these short and long wind barbs to represent even higher wind speeds. And then it goes even further. We can combine multiple pennants and multiple wind barbs to represent even higher wind speeds. So when we have 100 knots, that's represented by 2 pennants because each of those pennants represents 50 knots. And we can combine short barbs and long barbs to represent wind speeds greater than 100 knots. Now we can also tell what the wind direction is based on the orientation of the wind barbs. Now, the shaft that the barbs are connected to is going to point to the direction from which the winds are blowing. And this is going to be based on a 36-point compass, so that's why that compass is here for reference. Now, for an example, if that circle represents a station, then the orientation of the wind barbs in the staff shows that these winds are coming from 340 degrees, or from the north-northwest. Now, another example shows these winds coming from 40 degrees or from the northeast. So these would be northeasterly winds. And the last example shows winds coming from 190 degrees or from the south. So these would be considered southerly winds because they are coming from the south heading into the station, which is that circle. So that's how we can tell what the wind speed and wind direction is by looking at the wind barbs. So putting it all together, remember that pretty confusing, very intimidating Skew-T diagram that you saw in the beginning of this video? Well, now we can piece together each of the different lines and have a better understanding of what they all represent. So there's 2 basic lines plotted on a Skew-T from the data that is collected and calculated from the radiosonde. And from these 2 lines, we can derive a lot of information that gives us a better understanding of what's going on in the atmosphere and can also help us understand what weather to expect. Now, these lines are the temperature lines, which is the red line, and the dew point temperatures, which is the blue lines. Now, you'll notice that typically in the troposphere, which is the lowest layer of the atmosphere, your temperatures are decreasing with height. However, temperature inversions are where the air temperature remains the same or increases with height. So it's not always uniform and not always constant. So if you look at the 4 different items that are circled here, those are temperature inversions. That is where the air temperature is either remaining the same or it's increasing with height. Now we can also locate where the tropopause is, which is the boundary between the troposphere and the stratosphere, which is the second layer of the atmosphere. And in the stratosphere, temperatures typically increase with height. So you can notice this large temperature inversion, and that's how we can pinpoint where the tropopause is located. So now let's take a look at an example sounding. This sounding was observed at the Springfield, Missouri office on June 22nd of 2022 at 0Z, or 7 p.m. Central Daylight Time. Now looking at this sounding, you can easily point out the temperature and dew point lines, which is the red and green line respectively. Now, from these lines, we can derive a lot of information that can help us understand the atmosphere and what weather to expect. And you'll see all of this information at the bottom in those bottom charts. Now, one of those things that we can derive is known as CAPE, or convective available potential energy. Now, CAPE is where we have positive buoyancy, and that can help show us how unstable the atmosphere is. And when we use CAPE with all of this information that is derived from the radiosonde, we can then see if there's a chance for thunderstorms, how severe they'll get, and just a bunch of other great information. Now you'll also notice the wind staff, and you can see the various wind bars as you go up in the atmosphere. Now the wind staff can show us the storm relative helicity, the mean winds, and it can also show us the wind shear. And wind shear is just the change in either the wind speed or the wind direction with height. Now this can help us determine if the storms can then become severe, and it can help us determine a bunch of other great useful information. Now, a hodograph, which is in the top right corner, is a graphical representation of the wind speeds and directions with height. And depending on the shape of the hodograph can help us determine what specific storm mode we can potentially expect. For example, this study was from Wiseman and Klemp in 1986, and they found that when we have a very disorganized, very chaotic looking hodograph, that typically represents single cells or typical summertime pulse thunderstorms. They saw that when we have a straight line hodograph, like the middle image here, that typically represents the potential for multi-cell thunderstorms. And then lastly, when we have a curved hodograph, that can typically represent supercell thunderstorms. Now, this isn't for every case, and there's a lot more information that goes into determining storm modes and that goes into hodographs. So we're going to be looking deeper into hodographs and what they are and what they can show us in a future video. So make sure to stay tuned and check that one out in the future. So that concludes our video on SkewT soundings. So if you want more information, make sure to check out these websites. They give more information on soundings, and they also let you see real-time soundings across the United States. And definitely stay tuned for our next video, which is going to go over weather patterns. So thank you for tuning into the Weather Unlocked series, and make sure to stay tuned for future videos.